Okay, so let's get started. Today's session is boosting forecast accuracy with external data and AI techniques. And kind of moving right along, just to remind everyone, this is the third in a series. So if you haven't seen our previous two sessions, Mastering Time Series Forecasting and Choosing the Right AI Model for Time Series Forecasting, I'll direct you to the Ikigai website. In the resources section, all of these are available on demand. So if you want to go back and see what we've done so far, you're more than welcome. All right, so let's move on to the introductions. I'm really excited about our panel today. Some really great people from Ikigai. First, we have Dr. Jahangir Amjad, head of AI platform at Ikigai. So he brings a wealth of experience as a computer science lecturer at both Stanford and MIT. And prior to Ikigai, he earned a PhD in machine learning from MIT and has made significant contributions at Google, including work on distributed pipelines for statistical inference and the open source data commons project. We also have Abdullah Al-Omar. He's an ML engineer with a PhD in machine learning from MIT, and he's been recognized for his contributions to time series analysis, reinforcement learning, and causal inference. He recently earned the Inform's George B. Danstig Best Thesis Award. He's got second place for that and received the Best Paper Award from USENX NSDI. We also have today Ranjit Jose, who leads our applied AI and solutions team at Ikigai. He has extensive experience in go-to-market strategy and data-driven solutions. He's working with customers to drive transformative AI initiatives that empower enterprises to harness their data more effectively. So with that, I will kick it off to Jahangir, and we can jump into today's presentation.
Sounds good. Good morning or good evening, everyone, wherever you are. I'm very excited to be here. Let's just setting the platform for our discussion today. I think you've seen this, you're all aware of this. Hopefully, this is preaching to the choir. Time series forecasting is obviously, falls right into a very rich landscape of all kinds of data, the data that you may be interested in forecasting, and a bunch of other related data. And we have in this webinar series, previously we have covered, generic sort of what is time series forecasting. We've talked about how there is a set of algorithms. You can go from the statistical to the deep learning based to the modern transformer based versions, and then also graphical models all provide a different sort of view, have their different pros and cons in terms of when you might use one versus the other. Today, we'll focus less on the algorithms, and actually not at all on the algorithms, and more around, imagine you were happy with the algorithms that you're going to be choosing to forecast, whether it's a univariate forecast or a multi-dimensional forecast. What are other things that we can do to help your forecasts along the way? Because there is a lot of stuff that we can do, a lot of tools at our disposal. So I'll go through a brief overview of a few. This is by no means a exhaustive list. This is some of the stuff, some of the tools and techniques that are informed by our both academic and currently practical experience working with, across industry and academia in terms of the types of things that people do, types of things that we recommend, trying to boost forecast accuracy and explainability as as you dive into the world of forecasting in time series. As the topic for today is really just going to touch on some of those techniques. And I do want to mention that a lot of these techniques can be viewed as pre-processing techniques or at least pre-forecasting algorithm techniques. So we won't touch on the algorithms part. We'll touch on what you can do before you even get to that stage. So I'll focus on a few things here. We'll talk about missing data estimation and why that's important. We'll talk about anomaly detection. Some of you have obviously, I'm sure, dealt with that. We'll talk about change points detection, and then we'll dive deeper into incorporating spatial information. I'll make that more precise. And we'll also talk about auxiliary or external data, how to incorporate that potentially, and also how do you see the effect of your external or auxiliary data. And then we'll go into, I'll hand it over to Ranjit for a hands-on demo for how some of these things are possible with the Ikigai platform. But the early part of this conversation will mostly be generic and doesn't necessarily won't tie into the platform directly. So Missing data, I think we all know what that is. We all know that we have to be robust to it. Missing data specifically is, it's very common. It can happen when, if you have on this schematic here, every time series is its own column, x1, x2, x3. They could be related, they could not be related, just pictorial representing the fact that they could have missing data, missing point observations, really. They could be missing at random, or they could not be missing at random and be systematically missing. Systematic missing, as an example, if you're thinking of US Census, for instance, well, new counties are usually created and sometimes old counties get dissolved. In either case, when you don't have data about a particular entity anymore, or you started only receiving data at a particular point in time or after a particular year, that's systematic because the thing either doesn't exist anymore or didn't exist in the past. For modeling purposes, what we typically focus on is data missing at random. And we are not usually concerned with the systematically missing data because there might be other things that you can do to estimate systematically missing data. So when data is missing from your time series, whether at random or not, why is it useful to estimate those missing values? Well, there are some examples here. You might be interested in knowing the location of an object in space in between the pings that you actually receive. That might help you with your inference. You might be interested in the sales of a product at a specific store, which might either have delayed reporting or might be completely missing for one reason or another. And the important thing around missing data is that many existing time series forecasting libraries implementations might entirely ignore a series if a single data point is missing. That's not obviously the case across all of them, but it is a very common occurrence. And this can lead to a scenario where a lot of data which might otherwise be useful, is thrown out. And so missing data imputation or missing data estimation is a pretty important technique. And pretty important pre-processing thing that you might want to consider. There are many ways of dealing with missing data, especially the missing data at random. Some of these will be very obvious. You can linearly interpolate the missing data between observations that are observed. You can forward fill or backwards fill. Or in some cases, perhaps missing values could just be set to zero, especially if that's equal to zero means you never receive an observation. In some cases, that might make sense. In some cases, replacing it with the average or the mean or the median of what you do observe may make sense as well. And in some cases that we are very fond of, matrix estimation techniques, which has a very rich theory and practice, might be very useful as well. And I wanted to sort of pictorially represent missing data estimation through matrix estimation. On the left, you may have a bunch of time series, which may, in this case, be related to each other in some way, or may not be, may be completely independent. And then you have time on the rows. Missing data through matrix estimation is useful because matrix estimation allows us to sort of consider two dimensions and relationships that can be exploited across both the time series, so call it the spatial dimension, and the time dimension together without necessarily needing to do this independently for every series. And that's a very powerful sort of abstraction that allows you to consider more than just the evolution of time for individual series. I won't go into the details, but happy to take questions later. But there's a very, very vast, rich sort of domain of matrix estimation theory and practice that can be applied to a lot of these problems out of the box, and it performs really well with a lot of statistical guarantees in estimation as well. And so you can estimate missing data with a lot of different techniques. In Ikigai, you might see this later. This is an example with real data. Bureau of Labor Statistics makes median household income available across many US cities. Where you see two cities here, doesn't matter which they were. At two, sorry for the x-axis not being clear, that's years. And in the top one, you have 2 years of data missing, just not reported by the Bureau of Labor Statistics. And then in the bottom one, you have one of them missing. The lines that you see there were imputed lines. And so wherever you have an observation, you don't need imputation. Wherever you do, you would like to impute them. In this case, we used matrix estimation to impute them, but this is a very well-behaved couple of time series. So a lot of other techniques that I mentioned before would have equally worked well as well. So I just wanted to sort of ground this in reality around what does missing data imputation look like. So then later when you're forecasting, you can take the imputed data if you're confident that this looks good into account when you are actually forecasting. So in the interest of time, moving on to sort of anomalies, this will not surprise a lot of you. Anomaly detection is a pretty well understood domain. This is essentially talking about short-term deviations from the usual behavior. We'll talk about long-term sort of views later, but short-term is looking like a spike that you see in this particular pictorial representation. This could be useful in detecting fraud or unusual network activity, like you see something here, where in this example for a particular client of ours, we saw that a 2-hour system glitch showed 90% discount, causing the demand for that particular product to spike artificially. But of course, as you are thinking of forecasting, if that was a bug, you don't necessarily want to use that bug to bias how the future forecast would look like. And so you want to perhaps isolate that effect. And so how do you deal with anomalies? We are not going to sort of discuss how do you detect them. There are many statistical anomaly detection tools available. We have plenty of them available in Ikigai as well. Well, the one thing to highlight is that statistical anomalies may be explainable or may not be explainable. Usually we are after the ones that are surprising and not explainable, but sometimes they may have an explanation, in which case the question is it really an anomaly? It may be statistically an anomaly, but is it really an anomaly in terms of your expectations? So that leads us to many approaches of dealing with it when you're thinking of forecasting the future. Approach one is you want to maybe perhaps just remove the anomalous values altogether, especially when they were truly anomalous and unexpected and you don't have a good explanation for them. In that case, perhaps you want to use missing data imputation to be able to impute what the values would have been. And so it becomes a missing data problem before you forecast. Approach two is perhaps you have a way when you determine anomalies, you usually have a baseline to measure it against. And so usually, ideally, that would be an expected value. And so if you already have access to expected values which were used to determine whether something is an anomaly or not, perhaps you want to replace the anomalous value with the expected value, so that would be business as usual, ignoring the anomaly, especially when you're forecasting in the future. Or you may decide that this particular anomaly is a expected behavior. There may be other explanations for it that you're aware of. We'll discuss that later with when we talk about auxiliary data. So it may be a holiday effect. It may be like a known sort of a thing which is causing this quote unquote anomalous behavior. And you may want to take it into account when you are forecasting into the future. We'll deal with that later towards the end of when I stop talking, towards the end of that, and happy to take questions about that too. So the approach that you take, really, the bottom line is depends on what your domain is and what you really like to do. And so this is an entirely human in the loop evaluation as well. You can automate it later, but initially you would probably want to determine whether you believe that the anomalies you're seeing, the statistical anomalies, really do make sense as anomalies or not, and whether you want to ignore them or replace them or deal with them in that way. Here's an example of some data. This is public data available talking about life expectancy, yearly life expectancy across many countries. I took 5 of them, and essentially you see 1971 and 1993 to be the 2 anomalies. They shouldn't surprise you because they're short-term sort of dips in life expectancy. In 1971, it identifies Pakistan and Bangladesh. In 1993, it identifies Bosnia. If you know your history, you'll know that that is sadly not surprising. In 1971, Bangladesh and Pakistan used to be the same country, split into 2, and there was a big war, unfortunately leading to a lot of casualties. So that's why you see those unfortunate dips in life expectancy. And in Bosnia, of course, there was the war that was going on for at that time for a couple of years. And then that unfortunate dip in life expectancy is also entirely explained by what was going on. But statistically, those do stand out as anomalies. Sad example, but unfortunately, but from a platform perspective, when you are sort of testing out your anomaly detection techniques, at least you want those things to be surfaced. And so that was one. Pivoting a little bit to sort of from short-term changes into longer-term changes in behavior. So if the entire dynamic of a series changes, we call it a change point, and you want to ideally be able to detect that because perhaps the period before when things changed does not matter anymore. Think COVID as one example, where a lot of parents, at least for that period, not necessarily short term, really changed the dynamics of a lot of demand and sales that we observed during that time. People's behavior changed, at least for a slightly long lasting thing. And then post COVID, perhaps things returned to where they used to be or settled at a completely different point. But those are not anomalous shocks. Those are things that sort of you want to take into account in a slightly different way, and you want to give yourself a little bit of a time before you determine that yes, the dynamics of this particular series has probably completely changed. It is important because as I said, you may want to deal with it in several ways. If the dynamics have completely changed, perhaps, and you truly believe that the old ones are not relevant, the old behavior, then perhaps you want to detect this so that you can exclude all the data before the change point, so that you kind of determine that nothing that happened before really matters for the forecast that you're going to be doing, at least in the short term for the future. And of course, you could choose to completely ignore a change point as well, where you believe that perhaps that is something that you're going to observe in a cyclical manner, and it may not be short term, but it may come in phases. And in that case, perhaps you want the forecast to be sensitive to the fact that the series may have more than one sort of steady state behavior. So it really depends on how you want to choose those. In terms of the life expectancy example, I have this one example for South Africa, which is somewhere in the late 90s. We believe that there is a sort of a change point in terms of life expectancy. You notice that there is a gradual dip, and that sort of leads you to believe that there is the life expectancy has sort of settled around a very different sort of domain, in this particular case, a different regime. And unfortunately, as some of you will intuit, this was because in the 90s, South Africa had rampant AIDS epidemics, really. And a lot of people, unfortunately, were not living long enough. And that sort of steadily declined, or, well, rapidly, depending on your perspective, the overall life expectancy. So somewhere around the mid-late 90s, perhaps you wanted to update your view on where the life expectancy was trending in that particular country. And you could argue that now perhaps it's back, and then you can see there's another dip, which is a short-term dip due to COVID. If we extended this out, we would probably detect another couple of change points in there too. And so there could be multiple change points, and it really depends on how you want to use them and what your prior view on some of these things is. And then, of course, the main meat of the conversation here would center around spatial dimensions. So what we mean by spatial dimensions typically is other time series. So if you're interested in, say, the life expectancy in a particular country, well, other countries could be the spatial dimension. There are other series, and perhaps they are correlated, or perhaps there is a relationship between them that you might want to exploit. Or you could have other dimensions for the same country. Perhaps you have other metrics of interest which may be related to or contributing to life expectancy. And that also is what we will call a spatial sort of a dimension, because that is the other series that you may want to learn from when you're thinking of forecasting the series of interest to you. And in some cases, especially when there are other alternatives, like other countries with life expectancy, the word that is sometimes used in literature is longitudinal dimension. So as an example, if you have unemployment rate across 50 states in the US, well, those 50 states, you may be interested in one of the states that you're forecasting, maybe. The other 49 may be part of the longitudinal dimension here that you might want to learn from. Or you could also look at different sort of metrics for the same place or the same series. And then those could be part of your either multi-dimensional forecasting view or a longitudinal dimension. And so spatial relationships can be exploited because they're very useful when you think of looking at similarity. I'll describe that in a second next. You might want to cluster things because you believe that some things are similar, so they co-evolve. And perhaps when you're learning about what will happen into the future of your series of interest, maybe it's important to sort of identify what its cohort or its cluster of similar series really are, and that might give you a better chance of forecasting things in the future. And then, of course, something I won't cover in this particular presentation, But synthetic controls or the world of causal inference is another domain that you may want to consider, which might directly sort of establish relationships between different time series as a function of each other. And that might be in a more causal direction as well, where a particular change in a series may impact another series in a related sort of a way. We won't go into that today too much, but happy to sort of take questions around that. And I'll come back to sort of the matrix view as we study this a little deeper, which is very helpful because there are two dimensions here in a matrix view. Of course, you can extend it to a tensor as well, but for explainability, matrix with two dimensions, one dimension being the series, A, B, C, D, and E in this case, and the other dimension is time, which is the rows. And you can sort of eyeball it and see if I had to sort of figure out what appears to be similar to each other. A and B might be similar, and C and E might be similar, where D might be a completely different thing altogether. And so how do we sort of look into this? You can essentially plot A and B onto some axes. I'll make that more clear next, what those axes may be. Such that ideally you would like to see perhaps that A and B are closer on these axes and C is different from them. And then perhaps E is similar to C, and then similarity can then be encoded into perhaps a cluster. So that later on, when you're forecasting and learning from different series or doing a multidimensional forecast, maybe you want to pay special attention to A and B together and essentially do something separate for C and E, because now you have information that tells you that perhaps A and B don't as much inform what happens in C and E, and they mutually inform each other a lot better. So you may get better performance in your forecasting if you do this pre-processing. And so the question remains, how do we actually reduce time series into a structure or into dimensions which allow you to do these similarities and clustering? So we have a technique which is sort of well known, which is reducing a series into a vector, and they're already vectors, but you may want to reduce it to a smaller vector, depends on your choice. We call it time to vec. It's a fairly standard sort of terminology where you're reducing the time dimension for every series into a smaller vector, a dimension or a fixed vector dimension. And so when you reduce all those series into those, perhaps what you're seeing on the screen right now are first two dimensions of those vectors. And so in that sense, A and B tend to be closer than C because they're all fixed dimension vectors now. You can compute similarity on it. You can do cosine distances, or you can do Euclidean distances or something else as you choose fit for your domain, and essentially either find out what are similar. You can do nearest neighbors and find out similar series, or you could essentially cluster them based on that too. An added advantage is if your time series had a lot of history, you can compress them down into fixed size vectors, which maybe actually allow you to do compression because you may now represent everything in a more compressed form. And so you can compute the similarities over those embedding vectors. And another example in this particular case, this is a live example from one of our sort of use cases, which is every dot here on the top left represents on a three principal component level, represents every series. On the right, you see how those series sort of look like in a time series view. The regular time series view, and it would be very hard to sort of identify similarities there. There's a lot of noise going on too. But then on this bottom left, I am just choosing three of these series, three data points from the above, just to make this very clear. You see that the red and the blue ones appear to be closer together. And then you look at the right, at the bottom right, and you see, yeah, indeed, those red and the blue time series do tend to behave very similarly. And they are materially different from how the green time series is behaving, and which you see on the left, which is green being farther away from them. And so, that's the advantage of some of this, because when you are thinking of forecasting, perhaps these clusters will help you forecast a little better. You can think of new product launches, you can think of market changes, you can think of transitions where perhaps you have no data right now, but there are other properties that you can exploit to find what a similar cohort or a similar cluster to this thing that you're interested in forecasting is. And that may allow you to, even in the presence of no information around this series, you have a new product that you're about to launch, perhaps allow you to sort of project that out and forecast out into the future because you have helpful things in the cohort that you have seen in the past. So This brings me to the last topic, which is essentially how do you incorporate external or auxiliary or co-varying information? In the retail context, this is sort of easiest to explain and most natural, where you perhaps have sales data that you're looking to forecast into the future, but sales data could be very sensitive to other information, not other cities, other products, but perhaps promotions that you may be running or holidays, because they may impact things your sales numbers as well. So if you have those information or weather, which could also be a function as an example, of course, there are many other things. Interest rates could be another one. You view each of those other bits of information as time series as well. And ideally, you would want to provide that as input as well, where the forecasting takes the effect of those into account. So underneath the hood, you want algorithms that can essentially learn from those as well. And essentially take that effect into account when you're doing forecasting and really be able to adjust your forecast based on what's going on with those other things. The important thing here to know is, you could have holiday effect, you could have a Taylor Swift concert happening, which could impact a bunch of things, sales of your particular product or hotel rooms and things like that, and demand forecasting for those. Usually, a lot of this auxiliary data, especially holiday effect and special events and those sorts of things, are known ahead of time. So when you isolate their effect, you don't necessarily need to forecast them. You usually have a good idea of when they will be. You usually know what the holiday period is going to be. You typically know when you might be running promotions. And you usually might know when Taylor Swift might be performing in a particular place that might impact things. And so if you learn the effect in the future, you can easily know what's in the future and then use that to project out the forecast into the future. And then the final thing is, these are the last couple of slides that I have here to talk about how do we isolate the effect of these covariates or this external information. We haven't delved deeper into decomposition, but I think a lot of you know time series can be split into, sometimes an explainability view is isolating the seasonal effect, the effect of general trends, recency effect, and what is the idiosyncratic noise in the series, and then of course the covariate effect as well. To make it more clear, this is what it might look like. This is how it looks like in Ikigai, which you will see later on as well, which is on the top, you see perhaps what the real sales were. They were kind of very stable with some recent sort of idiosyncratic behavior in the short term. But then these peaks that appear to last for short periods of time and happening very frequently, and there is very little seasonal effect here. But you can split all of this down into different components. You see that the trend is pretty static, but that's really the one that is the baseline of this particular series. But then the blue things that you see at the bottom are essentially isolated effects of the covariates or the auxiliary data. In this case, it was mostly holidays. So holidays really tend to explain this big lift, Thanksgiving and Christmas, and Thanksgiving and Christmas and other sorts of things as well. And so not only do you want to be able to model external data, auxiliary data, covariate data, you also want to be able to then explain that effect. And usually decomposition views are very good at being able to isolate that particular effect. But if you are including covariate and auxiliary information, you want to be able to isolate that particular effect as well. So we have covered a few things that will each hopefully both help in forecasting if you know if your data sort of fits those particular domains, if it can help from missing data imputation, if you have decided that you can take out and remove anomalies, for example, or you've detected change points and now you want to only operate in the new regime. You will have other time series that you can learn from or cohort around or learn from based on similarity. And then, of course, if you have external data or auxiliary data that sometimes you even know into the future, which you're not interested in forecasting, but which may have an effect on the thing that you're thinking of forecasting, you may want to take that into account, especially when you are also looking at isolating the effect of some of those things in an explainable view. So I'll stop right here. I'll hand over to Ranjit, who may show you some of these things in action on the Ikigai platform as well.
Thanks, Jahangir. Great. Well, as Jahangir said, there's lots of advanced techniques that Ikigai makes available for you to be able to do your forecasting. And my plan is to give you a quick peek into how Ikigai makes this possible for you. But for anyone that's new to Ikigai, first of all, I wanted to make sure that you're able to see that everything that we do with the Ikigai platform in the end has to really help you from a business value perspective. For example, here you have the case of forecasting being done on an electronic manufacturer's products and being able to provide alerts to the operational folks such that they're able to see particular products that are about to be out of stock based on the forecast that Ikigai is generating for them is the kind of value that we want to make sure is available. Another a view of techniques being used to provide business value. We'll dig a little bit more into this later in my presentation, but at a high level, what you can see here is the time to vec or the time series to vector representation that Jahangir was just going through, helping analyze the promotions being offered to multiple products. And we'll dig a little bit more deeper into this later in the demo. But at a high level, how does Ikigai make this possible? So as you can see here, this is the Ikigai flow builder. This is what data scientists and technical folks on the back end would essentially configure for your own organizations, have the data come in. As you can see, we make it easy for you to be able to see all the data and have the data come in and then have all the outputs. I'll talk a little bit about how all of these are API enabled. But what you can see here is an example of historical sales coming together with historical temperature. So this is a great example of auxiliary data that has an effect on the sales being fed into AICast. This is essentially Ikigai's forecasting facet that's providing you the output, which is the demand. And each of these are available as facets, as you can see here on the top. So we just make it very easy for you to be able to not only manipulate data with a lot of the data prep sort of functionalities, but all the different advanced AI capabilities, including forecasting and some of the time series functionalities that we'll look at today are all available very easily for you here. And each of these, sort of facets comes with its own, with its own set of configurations. So in this case, for AI Cast, I'll just give you a quick peek how, each of these can be configured based on lots of different parameters. And obviously, Ikigai provides you training and documentation around how you would be choosing this. But these are the kind of configurations that you can easily make to have extremely powerful forecasting capability within your organization. But digging a little bit deeper into the time series functionality, as you can see, we make it possible for you to have a suite of time series functionalities. If I just keep going, you'll see what you have is anomaly detection, change point detection, embedding. These are just a few of the examples that Jahangir went through today. And I'll start with anomaly detection. As you can see here, it's a very simple flow that we have set up. You have your sales data going through the anomaly detection and then getting an anomaly output. How you use this within your flow, there are lots of different ways, but at a high level, what we're showcasing here is the ability for you to have your data go through the anomaly detection and then be able to have those anomalies automatically detected. Just like I mentioned, AI Cast anomaly detection also comes with its own set of configurations that you can configure. And here is an actual output of the exact same data set that Jahangir went through, an unfortunate example of how wars do affect life expectancy. And here you can see clearly anomalies being detected around the population of Pakistan and Bangladesh, and here around Bosnia. And so this is data sets that, obviously public data sets that we send through the Ikigai anomaly detection. It's automatically identifying for us, anomalies in the data. You can imagine how when you have vast amounts of sales data and other time series data, being able to quickly and easily and automatically identify this data in a manner that you're able to quickly then, as an expert, decide what you want to do with that data is something that Ikigai helps you with. Similar to that, going on to change point detection, that's again another facet or functionality from a data science or a data science builder's perspective, it's as simple as pulling this facet down, having the data connected to that, and then making a set of choices in terms of how you want to configure that. And then out of that, you essentially, again, another public data set, you get to see what a change point can look like. And here, as Jahangir was mentioning, in the case of South Africa, as they unfortunately went through their AIDS epidemic, you can clearly see how life expectancy changes. And you can imagine, in your own data set, being able to understand this in an automated way, how powerful that can be. And the final one I'm going to spend a little bit of time on is embeddings and cohorts, essentially to create the clusters of the cohorts that Jahangir was describing. You first go through creating the embeddings, and that's, again, a model that's available. You're able to just drag that into the flow builder, have your data connected to it, and then get the output. And what you're able to do with the particular configurations that you can make is essentially now power an application such as this. As Jahangir was mentioning, this is a case of multiple time series that are essentially going through, the embeddings facet, us being able to create the clusters, and then be able to run a business analysis on this. In this case, what we're trying to do is these are all the sales patterns over the course of a couple of years for electronics products through different channels. And what we're doing is we're essentially analyzing the promotions that are being offered for each of these products and identifying that there is this one particular product that is being offered a higher than normal promotion, while the sales performance of it looks very similar to products that are being offered lesser promotion. And so the analysis here is essentially driving us to the decision that you could be offering lower promotion while at the same time not losing any sales. And so these are the kind of analysis that you're able to do with some of these advanced techniques, where you're able to send vast amounts of data through these analysis and then be able to act on them in a very actionable way. And so here what you see is all of this data that essentially we're going to be analyzing in this case is time series data, which is essentially here similar in nature, that would show up as part of the same cohort. And finally, in the interest of making sure that we have enough time for Q&A, the last piece I'll say is that, from an input and output perspective, in terms of like all the flows that you set up within Ikigai, all of this are API sort of driven. You can have your visualizations within Ikigai itself, or just have the data sent to, within the tech stack of your organization, and have those visualization analysis done within the tech stack that you already have. So with that, I'll stop my piece and then pass it on back to Jahangir.
All right, thank you very much, Ranjit. This is great. I think we'll transition. We have 20 minutes remaining. Let's answer some questions that we've been receiving from you all. And for that, I would actually like to tap into one of my colleagues, Abdullah, who's here. I do want to mention quickly, I'd be remiss Abdullah has been a great asset to and a fantastic addition to our team over the past year. A lot of what you see, a lot of what Ranjit was showing as demos and what I talked about, some of that stuff is either coming right out of Abdullah's research and PhD, and Abdullah has actually helped implement some of those things too. So it is a great honor for us that Abdullah is here today as well. And before we key into some of the questions, I do want to mention how I know Abdullah. As I was transitioning out of my PhD time, Abdullah was a young student coming and starting his PhD. We overlapped a little bit like that, lots of conversations around time series. And he's obviously taken it to a completely different sort of level altogether, receiving a lot of acclaim for his work on time series data, forecasting, and some of the things that you heard about. I think Alex mentioned it in the beginning. He's recently, for his PhD thesis at MIT, he won the runner-up position out of hundreds of PhD theses at the very large Informs conference. It's usually attended by 7,000 people every year. And he won the George Dantzig PhD thesis runner-up award, which is a huge honor. And for those of you who know Dantzig, know know that there is no bigger name in the world of OR. And there was a huge honor for obviously Abdullah and for us to as a great source of pride. And he's also won a Best Paper Award for one of his time series works, actually, in the NSDI conference, which for those of you who know, that is the premier systems and networking conference across the world, really. And for time series techniques to be relevant in that domain too, I think is incredibly sort of useful and indicative of the fact that this data is everywhere. And some of what Abdullah sort of spends his time thinking about is obviously problems that are, domain agnostic in many ways. And so, Abdullah, my first maybe question to you, if you can let in on the audience, is what sort of inspired you or inspires you to work with time series data, and any sort of exciting insights you can share around your sort of years of involvement with this data and thinking about time series. If you took a step back from the algorithms, what might those nuggets be that you could share?
Yeah, I mean, I'll try my best to step back from the algorithm. I'm not sure if I will succeed, but I mean, the first time I actually dealt with time series was back in 2016, I think, or 17, where we were working on the task of demand forecasting for electricity consumption. And that was an interesting application of forecasting, specifically because you need to get the forecasting right. This is a very crucial application because in the domain of electricity generation, you have to generate exactly what you're consuming right now. So if you don't forecast well, that will translate into lots of loss in terms of dollars. And there is no safety stock in electricity. Of course there is, but in the more generic sense, you can't store energy in a cheap and efficient way. So that got me excited about time series, and maybe I'm gonna go a bit technical here, but the thing about time series, which is different than other classical machine learning problems, is that the data set has a sequential basically structure, and it's not what we call independent or IID data. So that's basically, you can think of time series as the like a more complicated version of classical machine learning. Like, how can you actually deal with this data that is not independent? For example, in the stock market, probably your best prediction for the price tomorrow is the price today. So can you actually do more than that? And this is like this sort of challenging question is what drove me into time series in particular, not a particular domain per se, but about like this nature of time series of this data.
Awesome, thank you. Alex, I think you may be able to tell us what the questions are that are coming in.
Yeah, thanks, Jahangir. Thanks, Abdullah. We've had a few questions come in, so I'll just kind of go through those. First is they saw a chart on decomposition that covered auxiliary. So could you kind of go through some of the other components of decomposition, like seasonality, trend? Should you just provide a little bit more color about how Ikigai does that?
Yeah, so one important way to understand time series is to understand these different components, or to decompose the time series into these different components. Seasonality will tell you, for example, how let's take a concrete examples here. For example, sales, right? How does your sale change? What are the periodic structure in your data in terms of the sales? Trend will give you will tell you something about, for example, the growth of your sales. Like, is it growing? Is it going up? Is it going down? What kind of growth or what kind of trend do you see in your data? And then the auxiliary effect, or the covariate effect, is basically what is the effect of all the internal or external aux data, something like holidays, promotions. So that this will help you, for example, in the case of promotion, to decompose the effect of, I mean, for example, if you have a promotion during the holidays, right? did my sales go up because of the seasonal effect that we expect people to buy more during the holidays, or is it because of the promotion that I actually added during the holidays? So all of these will actually help you help you make decisions, or more informed decisions in your company.
Cool, thank you. Another question coming in, how do you decide which external data sources to include in a forecasting model? And second part to this, is there a limit to the number of sources you can or should include?
Yeah. So there is no strict limit, but there is a trade-off, right? You do want to include the external data set that actually contribute to your sales, because it's easy to find series that are correlated, but they're not really, I mean, there's no causation here, and you don't really want to include all these. You don't want to overfit on your data. So there are two ways that one can decide which external data to use. The first one is tap into domain experts, and this is always very important. And we always also find it very important with our clients. We need to listen to them and see what they're using right now and what do they think affect their sales. I mean, they've been in the industry for a while, so tapping into that is still essential, even in the age of AI. The second thing that we can always do is that there are a lot of data-driven ways to select from like thousands of external factors. So we can always test and see which external factors actually we should keep, and there are lots of statistical tests for that. So the way I see it, at least the first method is the quick win here, because if you tap into the industry experts, they will basically give you a shortcut from their experience, when they've been dealing with this data for years. And in the second way, we'll also help experts actually identify things that maybe they didn't think of because it wasn't within their field of view.
Awesome. Okay, cool. Another question related to how Ikigai kind of handles this. How does Ikigai weight or prioritize different external factors? Could you explain a little bit more about how that works?
Yeah. So the way we do it, there are a lot of data-driven way to weigh these different external factors. For example, let's go back to the sales example, right? A sales for product for a specific product A, let's say, and then we've seen in the past how a specific promotion increased the sales of the specific product. So this is one way to basically look at the historical effects to give these different ways. But also, if this is a new product or if this is a new promotion that we haven't seen before, right? What can we do? Well, you can always look into basically something similar to the time to back that Jahangir mentioned, right? You can look at similar products that have seen that promotion, or similar products that have seen similar promotions, and all of these factors we take into account when we weigh these different external factors.
Now, just a question about kind of a specific question. Is our transactional data stored on the Ikigai platform to run the models?
Yeah, so that's a really good question. So I think if you're going to run models, if you're going to run algorithms, you have to have your data be available to the platform to be able to run it. You can choose to, obviously, we are SOC compliant and we have a bunch of other HIPAA certifications and whatnot. So hopefully there is going to never be a case where there is any kind of leakage of that data. It is only available to you to see. Nobody else can sort of take a look at it, for instance, even if they wanted to. If you were a large enterprise, then we could potentially work with you, and we have enterprise customers where we are deployed in their environment, in their VPC only. So the data, due to either privacy concerns or security concerns or volume concerns, may be required to stay within that particular VPC, and we can typically deploy our Ikigai platform within that VPC as well. That's a special handling. Obviously, that depends on the use case and what you want to do. But yes, in order for us to run a particular algorithm, you can choose to sort of filter it all out and only make available the data that is important for the modeling. You may choose to mask it for whatever is going to not reveal any PII or other things if you are so concerned. But nobody else should have access to that. You control access to the project, the data, the platform through which you are running your jobs. We call them flows. Hopefully that addressed and answered the question.
Cool. Thank you. I would say this is the last question that's come through. So, and it's a little more open-ended. It looks like we are wanting to explain more about the time to vec technique. So that may be newer for some folks on the call. So could you do a little bit of a deep dive into what exactly that is?
Yeah. So time to vec, what it does basically is for each time series that you have, can you get a sort of basically a representation that is like a compressed representation of the time series, such that you can do different different downstream tasks like cohorting. A more concrete example here would be, for example, you have the sales of different products and you want to relate these products to each other, right? Doing it on the time series level is really hard. You have lots of observation. I mean, doing it is computationally intensive. But what if I can actually represent this long time series, for example, in a two-dimensional vector or a three-dimensional vector? This will make different computational tasks much easier. For example, I can represent them into this two-dimensional space as Jahangir showed in his presentation, and then I can say, okay, product A and product B are actually similar. And then downstream task of that would be when I forecast product A, maybe I should look also into the dynamics of product B, or use maybe a lagged version of dynamics B as a feature in a more technical term. Yeah, so that's the objective of time to vec. I'm not sure if you want to add more to this, Jahangir.
No, I think that sounds good. I think the nice outcome of using the vectorized representation is it obviously allows us to have a unified sort of language and expression for all time series data. And it has natural connections to word to vec, which some of you would have definitely noticed. And later, I guess we can share the sort of white paper that Alex we have on the time to vec technique, how we use it, and the sort of parallels that it has with some of the sort of established other techniques like word to vec, which are very commonly used, and sort of really a lot of the heavy lifting that is going on in the large language modeling domain. We are obviously not in that language modeling domain, but this is the pre-processing that is required to do a bunch of other post-processing things, and to have that common set of language and tools, that vectorized representation for every series is extremely important here as well, to be able to do any kinds of advanced modeling, some of which we discussed earlier today. So perhaps we can share that as a outcome of this particular webinar as well.
Yeah, awesome. All right, well, that concludes our dialogue for today. So just a couple wrapping up items. You can register for the rest of the series if you haven't already. We've got a bunch more topics coming and more content that's on demand. And per Jahangir's point, we have a slew of resources that you can check out, focused on working with data science and business leaders, how to kind of bring the groups together for operationalizing AI, a deeper dive on time to vec if you have interest there, and then benchmarking and kind of a detailed analysis of how Ikigai handles time series forecasting. So I hope you enjoyed the conversation today. Thank you very much to our speakers and our panel. Always appreciate learning from you guys. So yeah, that'll include today's presentation. Thanks so much, everyone, for coming.